Hello, everyone. I'm going to go through some problems from your lab packet that addresses the metric, standard notation, scientific notation, pH, unknown variable, and some of the chemistry. Actually, I'm going to go through all of the chemistry problems. So let's first start with scientific notation versus standard notation. Well, the first problems that you see here, let me get my little markers. The first problems that you see here, I'm going to select a different color. Bear with me. There we go. These first problems that you're seeing here, we need to change from scientific notation to standard notation. Now, before I go through these, I want to address these values that are in the superscripted position, 10 to the minus 3, 10 to the minus 5 versus 10 to the 2. So what are you supposed to do with those numbers? First, I want to remind you of when you were in grade school. And probably in first grade, your teacher had a number line that was at the front of the classroom by the chalkboard or whiteboard. And the number line had 0 in the middle. And to the right of 0, the digits were positive values. And to the left of the 0, you learned those were negative values. Negative digits. So I want you to remember that. If positive, go to the right. If negative, go to the left. All right, so let's work some problems. How about we start with 9.82 times 10 to the 2? Well, the fact that times 10 to the 2, let's look at the value 2. That means we must move the decimal place 2 positions. Is that number 2 positive or negative? It is positive. So that means we need to move our decimal place 2 positions to the right. So 9.82 with the decimal point moved 2 positions to the right will now become 982 in the standard notation. Forgive my sloppy writing. It's a little difficult to actually write on a vertical screen. I'll try and make that better. Okay, what about 2.34 times 10 to the 10th? Let's do that one. Well, first we look at this number that is the superscripted number above the value 10. So we have 10 to the 10. Is that number positive or negative? It is in fact positive. And that means we will move our decimal point 10 positions to the right. Remember, right is positive. So now 2.34 becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've moved 10 places. That's where my new decimal point will go. And all of these happy faces fill in with zeros. So now our number becomes a very large number. a very large number. And this now raises the question, why do we even have standard notation versus scientific notation? If you were a scientist keeping a lab notebook, writing this very large number over and over again in your lab notebook would invite a mistake, dropping a 0, let's say. So you can appreciate why scientific notation is sort of like a shorthand version. I like to think of it as a large file that you want to send to a friend, and you zip the file. That means you compress it. And then the friend, when they get that zip file, they basically will download it and unzip it. So when we go from scientific notation to standard notation, think of that as unzipping the file. We are now going from a compressed version to an expanded version. Well, what about this 5.2 times 10 to the negative 3? Let's work on that one. Well, first of all, again, look at that number in the superscripted position. Is it negative or positive? It is negative. And remember, when it's negative, we go left. So now we have to move our decimal place 3 places to the left. What would that look like? One, 2, 3. Put in your new decimal place, fill in those happy smiles with zeros, and now our answer is 0.0052 for the standard notation. Let's do another one. 2.54 times 10 to the negative 5. Well, we again look at this superscripted number. It is negative. That means we need to move 5 positions to the left. This means 2.54, we write it out again, and we move 1, 2, 3, 4, 5. Put in your new decimal point, fill in those happy faces with zeros. And now we have 0.0000254. But how do we send these large or small numbers in a zip type format? How do we go from standard notation to scientific? Again, think of that as taking a very large file and compressing it as a zip file so that you can send it over email to your friend. So let's cover 987,000. Okay, let's do a new slide here. Here we are. 987,000. Okay, let's write that without any commas. But where is the decimal point? Right here. Now, to send this number in scientific notation as a compressed zip file, if you will, using my analogy, we must move the decimal point so that we only have one number to the left of the decimal point that is between the number 1 and 9. So we now need to move our decimal point 1, 2, 3, 4, 5 times. And this now becomes 9.87 times 10 to the 5th. Now, should that number 5 have a positive value or a negative value in front of it? Think of how you want your friend that you're sending this compressed file. You need to send instructions on how to unzip the file. How does your friend get back to the original value? Well, does your friend need to move the decimal point to the right or to the left to keep the original value? Your friend would have to move the decimal point to the right to get back to the original standard notation. So that means you keep this value positive. What about 0.567? Let's do that one. Well, again, we need to move our decimal place so that we have one digit to the left of the decimal point between 1 and 9, or to 1 and 9. So we just need to move our decimal place one position. And now we get 5.67 times 10. Well, why do we say times 10? Let's cover that. Because we jumped by a 10, right? We moved the decimal place. When we're moving the decimal place, it's a jump of 10. So we need, again, these are part of the instructions to tell our friend how to unzip the file. So we move by a decimal place, that's a value of 10. Which way did we move? Or how many places, I should say, did we move? We moved one place. Okay, we need to leave more instructions to our friend on how to unzip this file. How can they get back to the original value? Well, now we need to tell our friend that they would have to move the decimal place to the left. And remember, left side, the digits on the left side of 0 in our number line, they are negative. So we would put a -1, and that would tell our friend that they need to move the decimal place to one side, or sorry, to the left, one place, one jump. Lastly, let's cover 8.75. 8.75. How do you put that in scientific notation? It's not in scientific notation, it's in standard. And you might be saying, well, Kara, there's already just one digit from 1 to 9 to the left of the decimal place. What more could we do to this? Well, we need to put it in scientific notation. We would still say 8.75 times 10, but how many places should our friend move that decimal place? Should it be moved at all? Did you say, no, it shouldn't be moved? Well, then you tell your friend, you don't move it at all by putting a 0 in the superscripted position above 10. So that is how we convert from scientific notation to standard notation. Now we move on to the metric system. First of all, some of the problems in your lab manual ask you to convert from CC into some other unit value. First of all, many of you might know that a CC stands for a cubic centimeter. And that means when we say a cubic centimeter, we have 1 centimeter in width, 1 centimeter in length, and 1 centimeter in height. That's what we mean by a cubic centimeter. And if we were to put water into that prism, into that 1 centimeter by 1 centimeter by 1 centimeter, 1 milliliter, which is a type of volume, would be able to fit in that prism. Next, how can you convert from one metric unit to another? For sure, those of you who are comfortable in dimensional analysis, you can use dimensional analysis. But some of you are not comfortable with dimensional analysis. You might not know what all those prefixes mean in the metric system. You might not know that deci means a tenth. You might not know that centi means 100th. You might not know that milli means 1,000th. And you might not know that deca means 10 times more, or hecto means 100 times more, or kilo means 1,000 times more. Sometimes I like to have fun with my students. Excuse me. And I like to ask them, would you like to have $1 or a kilo dollars? And they think that's funny. They entertain me. They placate me. They laugh at my stupid jokes. So maybe you might not know your prefixes. You might not be very strong in your dimensional analysis. Well, I'm going to introduce you to the King Henry slider, shown here. First, let me explain the B in the King Henry slider. This is your base unit. A base unit can be something like a volume. Well, the base unit for volume would be a liter. The base unit for length would be the meter. So base units, let's write this. For volume, it's liter. For distance, it's meter. For time, it's second. And for mass, it's gram. And for some of you, you might have Professor Marcelo Pires as your instructor. Different countries abbreviate gram. Some of them might put GM. So you might see that in some of your slides on some of the problems, and some students get confused, G or GM. So that's our base unit. Now, King Henry slider, why do we call it that? It's because there is an acronym to remember all of these letters in order. They go from left to right. And I'm going to underline in yellow, King Henry died by, and the word by is our base unit, drinking chocolate milk under 9 pink flamingos. What a horrible way to die, by drinking chocolate milk under 9 pink flamingos. It's a silly acronym, I understand, but it will get you through. Now, before I move forward, I want you to see something here very important. Notice after the M, the milli or milk in our King Henry slider, we have dot, dot, then U, dot, dot, then N, dot, dot, then P, dot, dot, then F. Most of the time, our metric system jumps in values of 10. However, after milli, the next unit is micro, and the symbol mu is the symbol for micro. It's a U. But it's no longer a jump of 10. It's a jump of 1, 2, 3. It's a jump of 1,000. And same thing between micro and nano. It's another jump of 1,000. And between nano and pico, it's another jump of 1,000. And between nano and femto, it's another jump of 1,000. So I put those 2 dots in between as placeholders. What do I mean by that? How do we use this King Henry slider? Well, let's work some problems. Here's our King Henry slider. Let's work on this very first problem right here. We need to go from 35,000 micrometers to millimeters. First step, I'm going to go through the steps. Our first step is identify your starting position. So we want to start from micro. Here's our starting position. Next step, identify your ending position. By position, I mean where you would be on the King Henry slider. So this is our ending position for this first problem. Next step, count your jumps. What do I mean by that? Count how many spots you need to jump to get from your starting position to your ending. So here we go. I need to go 1, 2, 3 positions. Remember, between micro, our starting position, and milli, there are two little dots that I put there for placement holders. Each dot must be counted. It represents a jump of 10. So in our case, we needed to jump 3 times. Oops. 3 jumps. Okay, so let's do that. Let's rewrite this. 3, 5, 0, 0, 0. It's not written, but where is the decimal point? It's at the end of this number. So I need to jump 3 positions. Which way do I need to jump? Count your jumps. And our next step is which way did you jump? Well, we need to jump to the left. Again, 1, 2, 3. So let's jump 3 positions to the left. 1, 2, 3. And that means 35,000 microliters equals 35 millimeters. So 35,000 micrometers equals 35 millimeters. Well, here's another fun thing to do. Can you put this number into scientific notation? Can you do that? It would be 3.5 times 10 to the 1, as we learned in our previous segment. What about the rest of these? Let me just highlight a few of them. Let's first insert a new slide. There we go. Let's do this one, the 1 second to nanosecond. Let's do that one next. 1 second to nanosecond. Okay, well, our King Henry slider, maybe we should write that again. Excuse the traffic. Okay, so we're going to go from 1 second to nanosecond. Well, our first job is to identify our starting position, and we're starting at our base unit. Our second job is to identify our ending position. Our next step is to count the jumps and be mindful of the direction. 1, 2, 3, 4, 5, 6, 7, 8, 9. We jumped 9 positions to the right. So 1 second looks like this if I were to include the decimal point. And now I jump 9 positions to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where my new decimal point should go. Fill in all those happy faces with zeros. And we get a very large number. Again, as you heard in my scientific versus standard notation discussion, writing this very large number over and over and over again is going to invite a mistake. Someone will drop a 0. And then that means all of your experiments are now going to be wrong when you're trying to publish this information to the world. So standard notation invites mistakes. How can we convert this very large number to scientific notation? Well, we need to compress our file. We need to turn this large file into a compressed zip file. What do? Move the decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9 positions to the left until we get a number, one digit to the left of the decimal place from 1 to 9. So this would now be 1.0 times 10. How many positions did we jump? 9. What symbol, positive or negative, should we put in front of that superscripted 9 to tell our friend how to unzip the file? We want our friend to move the decimal place back to the right. Remember, digits to the right, then our superscripted number would be positive. So on your chemistry metric exam worth 5% of your total grade, this portion of the exam is likely going to be multiple choice. And if I asked you to convert 1 second to nanoseconds, this very large number that you're seeing here probably will not be an answer choice for you. But this scientific notation answer choice will be an option. What's the beauty in this type of testing format? It means not only can your professor test your ability to convert from one metric unit to another, but also at the same time, can you convert that answer into scientific notation? Let's do one more. How about we do the 740 cc's into a liter? Okay, so let's write that down. we're working on 740 cc's to 1 liter. Now remember, a cc equals a milliliter. So our first task is to identify milliliter. There it is. Our next task is to identify our stopping point, our finishing position. And that's our base unit of liter. Our next task is to measure how many places we jump. So I'm going to jump 1, 2, 3 positions to the left. And that means I rewrite the number with the decimal point, and I jump 1, 2, 3 positions to the left. So 740 cubic centimeters, cc's, which are milliliters, will equal 0.740 liters. Now again, turn that into scientific notation. This would be 7.40 times 10 to the -1, because that tells our friend to unzip this compressed file 1 decimal place to the left, and they know it's to the left because the negative superscripted value. Again, cc equals cubic centimeter, and a cubic centimeter would have the volume of 1 milliliter. So I'm going to move on. You have the answers to this section of your lab manual, and I think just a couple examples that I've done is good enough to get you through how to use the King-Henry slider. Let's go on to graphs and proportionality. The equation that you're going to use for these graphs and proportionality problems involves x1 over y1 equals x2 over y2. In your lab manual, you are given this graph. Well, it's not very obvious to some students initially that from this graph, you are expected to get your own x1 and y1. So I'm just going to pick one x1 and one y1. I'm going to use x of 8. And I see when x is 8, y is 40. Okay, so if x is 8, y is 40. All right, let's solve these problems. If x1 is 8 and y1 is 40, then what is x if y is 65? And if you notice, this now becomes the same types of problems that you saw above this graph in your lab manual, where you're again solving proportionality. How do you solve this? You cross multiply. So if I cross multiply, I get x times 40 equals 8 times 65. So if I have that, then x would equal 8 times 65 divided by 40. I just do the math, 8 times 65 divided by 40, and I get 13. So x2 would be 13. We can do the same type of cross multiplication for these other proportionality problems. Again, cross multiply. X times 3,400 would equal 2,300 times 200. Solve for x. Well, I would have to divide both sides by 3,400. And now I get 2,300 times 200 divided by 3,400, and I get 135.29. There are other problems in your lab manual that also discuss this proportionality. In this example shown here with D1 over T1 equals D2 over T2, we're now addressing velocity. So distance over time. A change in distance over time is velocity, a way to describe speed. So here we have our distance, millimeters, over time, seconds. So we want to know if we have a paper speed of 25 millimeters per second, how far will we go if we travel for 2 seconds in time? This is a proportionality problem all over again, and it means we cross multiply. We now have x times s equals 25 millimeters times 2 seconds. Divide by s, and now we get x equals 50 millimeters. What about the second problem? Paper speed of 20 millimeters per second. And what is the time if we have 13 millimeters of recording? Okay, so now we have 20 millimeters per second equals 13 millimeters. And we now need to solve for the time. It's a proportionality problem. So we get 13s equals 20 millimeter times T2. Divide by 20 millimeter on both sides. And I should say that this is 13 millimeters. The millimeters cancel out. And our T2 equals 0.65 seconds. What about this third problem? What is the paper speed of an output that received 1,020 linear millimeters of recorded tracings during 17 seconds? Well, this is no longer a proportionality problem. This simply means you're trying to find out the speed. So it's change of distance divided by time. And now we get 60 millimeters per second. Now in problem 4 on this D1 over T1 equals D2 over T2 portion of your lab manual, you are shown a picture of a tracing from an EKG machine. And you are told that the distance X corresponds to 16.5 millimeters. So I'll do this over here in the corner. And also in problem 4, you're told that the paper speed is 25 millimeters per second. And you're told that the distance shown in the picture is 16.5 millimeters. Solve for time. It's again cross multiplication. So you're going to have T2 equals 16.5 times S, and that 16.5 is millimeters, divided by 25 millimeters. The millimeter units cancel, and all we have to do is divide 16.5 by 25, and our time is 0.66 seconds. Let's move on to our chemistry section. Okay. First problem. How many grams of sodium chloride would you use to make 100 milliliters of a 4 molar solution? Let's remember that 4 molar means moles over a liter of solution. How do we convert? How do we even tackle this problem? Well, first start with what you want. In this problem, we want 4 moles per liter. And another way of writing that would be 4 moles per 1,000 milliliters. There are 1,000 milliliters per liter. How do I know that? How can I prove it to you? Let's go to our King Henry slider. If my base unit is liter, and I have 1 liter, how many milliliters are there? Well, I want to go to milli. So I would move 3 places, 1, 2, 3 to the right. So that would be 1,000 milliliters. So our King Henry slider is so useful in other places besides just our metric system conversion. Okay, so now I know I want 4 moles for every 1,000 milliliters. Okay, so now I need to know that the molecular weight of sodium chloride is 58.45. That is not something you need to remember. I will give that to you on your exam. So there are, for every 1 mole, I have 58.45 grams. My mole values cancel out, and I am left with 233.8 grams for every 1,000 milliliters. But I don't need 1,000 milliliters. I only need 100. Okay, so I only need 100 milliliters. My milliliters will cancel out. 100 goes into 1,000 10 times. I only need 1/10 of this volume. And that means if I divide 233.8 by 10, I get 23.38 grams that I need for every 100 milliliters. What about this second problem? Well, first, the molecular weight of glucose equals 180 grams per mole. Again, you don't need to memorize that. That is my job to tell you. So how do I set this up? Well, first of all, this looks scary, 2 millimolar. That means 2 millimoles per liter of solution. What's another way I can write that? I should convert it to just moles. Well, what are 2 millimoles in moles? Again, I can use my King Henry slider, and I move my decimal place 3 places to the left when I use that. So 2 millimoles now equals 0.002 moles per liter of solution. Now I multiply by 180 grams per mole, which is the molecular weight of glucose. And just like that, I am told that I need 0.36 grams per liter of glucose to make a 2 millimolar solution. What about the next problem? What is the molal in grams percent concentration of a solution of 20 grams of sodium chloride in a total volume of 100 milliliters of water? Well, let's start with the grams percent concentration. gram percent means how many grams do you have in 100 milliliters of solution? Well, we're told we're putting 20 grams in 100 milliliters. So that's easy. We have 20 grams in 100 milliliters. That means we have a 20 grams percent solution. Now, the more challenging problem is calculating molal. Molal is the number of moles per kilogram of solvent. Now that's different than molarity. So molarity is number of moles per liter of solution. These are different things. However, in our classroom, we are using water as a solvent. And we are calculating very dilute solutions. So for us in this class only, don't ever do this in a chemistry class, we have license to switch from molarity to molality because we're playing with water. And 1 kilogram of water has a volume of 1 liter. And again, this is unique to our class because we are only playing with water as our solvent. You are in human physiology, and we are mostly water. We are walking sacks of dilute aqueous solutions, as I like to joke about in class. So let's start this. We know that we are starting with a 20 grams percent solution. Let's start with that. That means 20 grams per 100 milliliters of water. Let's first start by converting our 100 milliliters into our base unit, liter. There are 1,000 milliliters for every 1 liter, and you can use your King Henry slider to prove that to yourself. Our units cancel. 100 goes into 1,000 10 times. And now I have 200 grams per liter. Now let's convert our grams to molecular weight, or to moles, I should say, using molecular weight. For every 58.45 grams of sodium chloride, that is 1 mole. And if I do that, and I divide our 200 grams by 54.45, I now have 3.42 moles per liter. Now that's molarity. I need molality. And because I'm playing with water, for every 1 liter of water, it has a mass of 1 kilogram. Again, don't ever do this conversion in a chemistry class because you're not necessarily only playing with water as a solvent. And these calculations would be very different in a chemistry class. My units cancel out, and now I have 3.42 moles per kilogram of solvent. What about this problem? How would I make 400 milliliters of a 3% glucose solution? Well, start with what you have. I have 3 grams in 100 milliliters. How much do I want? I want 400. You know, this is a lot like if you were making chocolate chip cookies and you're following the directions for 1 batch, which gives you 24 cookies, let's say. Let's say you want to make 4 batches. What would you do to every part of the ingredients list? You would multiply by 4, wouldn't you? Well, that's exactly what we're doing. We want 400 milliliters. So that means if I want to make 4 batches of this 3 grams percent solution, I'm going to need 12 grams total of glucose. That was pretty easy.